everyone, welcome to part 1 of chapter 4. Today begins our math-heavy chapter. This is the first chapter we've come across in this class where we really need to incorporate math into chemistry. Chemistry, you can kind of think of as an applied math class, right? We do a lot with, chemical bonding and, nomenclature and things like that, but a large portion of chemistry is measuring amounts of things. How much did we start with in this reaction? How much did we get? What percent yield, right? How do we make a measurement? All of that kind of stuff. So this chapter begins our talks on measurement. How accurately do we measure things? So today we are going to look at measurements, and we're also going to look at significant figures. How accurately can we report a number? And then we're also going to look at scientific notation toward the end. So a lot of this is just kind of setting up our mathematical skills so that we can use math in chemistry moving forward. So let's go ahead and get started. So in chemistry, we make a lot of measurements. Whether this measurement is with a ruler or a graduated cylinder or with a balance, we make measurements. And these measurements are called quantitative observations. In previous lectures, we talked about what's called qualitative observations. I notice a color change or bubbles being formed or light being produced, right? And those are qualitative. We describe them with words. But quantitative observations are when we describe things with numbers. So like 1 cup or 3 eggs or 5 molecules, things like that. When you make a measurement of any kind, you always need to have a numerical value, so some kind of number, and also the unit of the measurement. That's really important. So like here, we have our number and our unit, our number and our unit, and our number and our unit, right? Over and over and over again. In chemistry, you must always put a number and a unit. If you leave your unit off, I will mark it wrong. So I'm going to say that again. Just a heads up. If you leave the unit off of your answer, I will mark it wrong. Maybe not completely wrong, but you will definitely lose points. Without a unit, our numbers have no meaning. If you just write down 3 what? 3 feet, 3 miles, 3 inches, 3 grams? I have no idea what 3 you mean. So you always need to put a unit after it to have your numbers make sense. So for example, say our answer was 50 kilometers. Well, there's our number and there's our unit. So I always have to put a unit. So we have different types of numbers in this class. And I know that's going to sound a little bit silly, but our first type of number is what's called an exact number. An exact number is one that results from 2 different situations. It's either a counting number or one that results from a definition. So when we are counting things, let's say I have 3 cats. I do have 3 cats. I know it makes me sound like a crazy cat lady. My husband had 1 cat. I had 2 cats. Now we have 3 cats. But when I count these cats, I have exactly 3 cats, right? I have 3.000000 cats, right? Even though they're really fat, there's still 3 cats. I can count them. I'm kind of like people in a classroom, right? I can count them. So these are exact numbers. There are exactly 20 people in the room. Okay. They also have, ones by definition would be something like 1 liter is exactly 1,000 milliliters. So those are ones that result from a definition. And we'll talk more about that later. But a large part of today's lecture is going to talk about significant figures. Okay. And for exact numbers, they have what's called an infinite number of significant figures because they are exact. So like if I have 3 cats, I have 3.000000000 and on and on and on cats. So when we look at significant figures later, these exact numbers won't play into our significant figure calculations because they are exact. Most of the time in chemistry, we deal with what's called measured numbers. Whether we're using a ruler or graduated cylinder or a balance, right? We're making some kind of measurement. And these measured numbers have some kind of uncertainty with them. Even if we measure things really precisely, there's always going to be some kind of uncertainty because nothing can ever measure an infinite number of decimal points, right? At some point that, those decimal points stop and we have some uncertainty, okay? So for example, when we are reporting the length of an object, And we're going to look at some examples here. You're going to observe the numerical values, the marked lines at the end of the object, and then you're going to make an estimate of the last digit. And you're going to visually kind of divide up the space between between the smallest lines and make an estimate as to one more digit. And that estimated number is the final digit that's being reported for a measured number. So you're going to have a bunch of numbers that you know for sure, and then one digit that you are going to estimate, which is why these measured numbers always have some kind of uncertainty, because they require an estimate at the very end. Even if we have, like the balances that measure mass in the back of our classroom, right, in our back of our lab, even those are making an estimate. That last digit is a guess. So you'll notice the last digit may change when you weigh some things out, and that's because your scale is trying to help make a guess, okay? So for example, if we look, like here's a stick, and we're using a ruler to measure it. Do you see that our stick ends somewhere between the 4 and the 5? Okay, so we're not going to say it's 4 centimeters because it's definitely not. It's definitely not 5 centimeters, but it's somewhere in the middle. So we are going to estimate one digit, and I will say this a lot of times. We're going to estimate one digit past what we have a line for. So do you see we have a line at 4 and we have a line at 5? So we're not going to write down 4 or 5 as our answer. It's going to be 4 point something. And that something is going to be a guess. Here I've guessed 4.5. But I just as easily could have said 4.4 or 4.6 or something like that, right? Because we don't know that this is at 4.5. We just know that it's somewhere between 4 and 5. So that last digit, this 0.5 or 0.4 or 0.6, that last digit is an estimate. We're guessing, okay? So in a measured number, anytime you're making a measurement, there's always going to be that last digit that's an estimate. Let's try this one. I found a better ruler. Right? I was like, 4.5 isn't good enough. Let's get a better ruler. So now, instead of just being 4 or 5, we have the tenths markings in between. Okay? So now, if we look really closely, right here, do you see it's actually somewhere between 4.5 and 4.6? Right? So now, we're looking even closer. It's somewhere kind of in the middle here. And so we say, okay, we have a line for 4.5, and we have a line for 4.6, so we're going to estimate one digit past those. We're going to estimate to the hundredths. Okay, so it's going to be 4.5 something to show that it's somewhere between 4.5 and 4.6. So here I put 4.55, but we just as easily could have put 4.56, 4.57, right? Anything like that, depending on how you're reading it. Right? This is all going to be up to you as an individual. Your lab partner may get a different answer than you, right? You may have written down 4.55 and your lab partner may have written down 4.56 based on how you're reading it. Both answers would be correct because we know it's just somewhere between 4.5 and 4.6. So we're estimating that last digit, okay? But let's say, for this example, that now we have something that looks like it's exactly at 3 centimeters, right? So it's not between 3 and 4. It's exactly on the 3 line. But if you write down 3 centimeters, then I'm going to tell you that you're wrong. Because do you see that we have a line for 3 centimeters? If you have a line for that number, then you need to estimate one digit past that. To say that we think it's exactly on the 3, we say that this is going to be 3.0. Okay, because again, we have a line for 3 and we have a line for 4. So it needs to be 3 point something. And to indicate that we think it's exactly 3, we write 3.0. That's telling us we think it's exactly on that 3 line. Okay, but again, we're always going to estimate one digit past what we have a line for. Since we have a line at 3, we can't say that it's 3 centimeters. We're going to estimate one digit past that and write 3.0 centimeters. But you could have, like I said, you could have said 3.1 or maybe even 2.9, right? Because it's an estimate. So let's try this, okay? And I know that this is a bit weird to read, but let's say this is, that's 8, 8.5, 9, 9.5, 10, etc. Okay, and these little markings are in between, so 9.1, 9.2, 9.3, etc. Okay, and I want to know, what is the length of the red line? So go ahead, pause here, think about this, and come back when you're ready to see the answer. Alrighty, let's go over this. So right off the bat, do you see this is 9, 9.1, 9.2, 9.3, 9.4, 9.5, right? So it can't be 9.1 because I have a line for 9.1. So automatically it can't be 9.1. So is it 9.13 or 9.14? And the answer is, could be either one, right? Because we know it's somewhere between 9.1 and 9.2. So it could be 9.13 or it could be 9.14, it could be 9.15, right? As long as it's 9.1 something to indicate that it's somewhere between 9.1 and 9.2, okay? So these answers could be different as long as you have the right number of digits, okay? So that's showing us the precision. It's showing us how accurately we know something. So we can do the same thing with graduated cylinders. So let's look at this. So this is 50, right? This would be our 50 line. This is 50.1, 50.2, 50.3. Do you see it's somewhere between, oh, sorry, this is 50, my apologies, 51, 52, 53. Sorry about that. But do you see that it's somewhere between 52 and 53? So again, we can't write down 52, we can't write down 53 because we have lines for those. We're going to estimate one digit past that. It looks like it's very, very close to 53, so I wrote down 52.9 milliliters. Okay, always a number and a unit. So here on this one, do you see it's somewhere between, this is our 11 mark, right? And that looks like it's exactly on the 11.5 right there. We're always, sorry, I should talk about reading graduated cylinders. So this is a graduated cylinder. It's how we measure liquids, right? And we always measure from the bottom of the meniscus. You have to kind of bend down, put your eyes at the level of the water, and you're going to read directly from the bottom, not from the top. So when we read this here, it's not at the 11 mark. This is the 11 mark. But it looks like it's exactly on that 11.5 mark. But since we have a line for 11.5, we can't say 11.5 because that's not precise enough. If we think it's exactly on the 11.5 line, we put 11.50 to say, oh, I think it's exactly on the 11.5. And then again, milliliters for our unit. Okay, so we can do this not only with rulers, but we can also do this with graduated cylinders. The cool thing is, when you're using the balances in the back of the classroom to measure mass, they're already doing this estimating for you. So you don't need to do this whole reading, one place past the smallest mark. You're just going to write down whatever the balance said. It already made the estimate on your behalf. Okay. All right. So let's go ahead and get some practice. I want you to do problems number 1 through 4 on the Chapter 4 lecture worksheet. Once you're done, come on back and we'll keep going. Alrighty, so like I've said before, every time we're making a measurement, we are estimating one more digit, right? We're going to estimate one digit past what we have a line for. So since we're doing this estimation, we're always going to have uncertainty in our measurements. That last digit is always going to be uncertain because that last digit was estimated, right? Was it 5.52, 5.53, 5.2, and so on. We're making an estimate, so we have some amount of uncertainty. The other digits, all of the other ones, not the last one, but all of the other ones, those are certain digits. So it doesn't matter if I read it or your lab partner read it or you read it, we would all come up with the same answer for all of the other digits. But that last digit, that last one is estimated. Okay, so anytime we're making some kind of measurement, whether it's you making the measurement or the balances in the back of the room, anytime a measurement is being taken, there is some amount of uncertainty. These are not exact. The only time we're going to have exact numbers is when we actually go through and count things, like people in the room, or like I said, number of cats, right? Those are the only time we're getting exact. Otherwise, if we're measuring anything, we are going to have uncertainty. So like I said, we're always going to have our certain digits and one last digit that's being estimated. Only one though. You can't estimate more digits than that, just one estimated digit. So because of this whole uncertainty business, our measurement is going to be limited by how many digits we can report. right? Can we say it's 52.0 milliliters or 52.00 milliliters, right? It depends on how many lines there are on our graduated cylinder and how much we can estimate. Okay, so all of this measurement and uncertainty is going to limit how many digits we can report. And so these digits that we're reporting are called significant figures. Okay, they show us how accurately we are making this measurement. For example, if we look at this thermometer, right, and we measured this, it looks like, it's exactly on this 22 line. So again, since we can't write 22 as our answer, to say it's exactly on that line, we say 22.0 degrees Celsius, okay, to show that we think it's exactly on that 22. So it has 3 significant figures, 1, 2, 3, and this last one is uncertain. Here though, if we go and we get a better thermometer, one that has more lines. Do you see this has better increments than this one? If it has more increments, right, more little lines, this one is going to be more precise because we can record our answer to more significant figures. Because now when we see, okay, it's actually not on the 22, it's just past 22.1. It's actually somewhere between 22.1 and 22.2. So we are going to estimate this last digit here to say 22.11. Okay, again, we're always going to estimate one past what we have a line for. So since we actually have a line for 22.1, we're going to make one estimated digit past that. So now there are 4 significant figures, with the last one being uncertain. Okay, so this one has 3 significant figures and this one has 4. So this one is better, more precise, and it's because we have more lines on our measuring tool. Okay, so depending on what we're using, right, depending on how precise our tool is, we can get better precision in our measurements. So significant figures. These significant figures, they are digits, so numbers that convey the precision with which a number is known. More significant figures equals more precise. Okay, so like here, where we had 4 digits as opposed to 3, this was more precise because we had more significant figures. Okay, there are rules that can be used to tell us which numbers are significant and which ones are not. Okay, so this is important. Just because all of these numbers show up in a measurement doesn't mean they are all significant. This is where it gets exciting. Here we go. Here's our rules for counting significant figures. Any non-zero digits are significant. So those are all the numbers 1 through 9. Those are always significant. It's just the zeros that sometimes are and sometimes aren't. Like I said before, though, some numbers have an infinite number of significant figures. And you'll hear me say sig figs because it's shorter. So if we have, 3 cats, right? Those are the ones that have an infinite number of significant figures. I counted 1, 2, 3. I have 3 cats. I have exactly 3 cats. So they have an infinite number of significant figures. Also, things by definition, like there are exactly 12 inches in 1 foot. Exactly. So anything by definition, that will also be exact. And these exact numbers have no uncertainty. Okay? So like I said before, anything 1 through 9, they are significant, but these zeros are the ones that are sometimes significant and sometimes not. And the zeros are what throw people off. So zeros are significant when they are between non-zero digits. So I call these captive zeros. They've been captured by other numbers. So like 75.04, do you see this 0 has been captured by the 7, the 5, and the 4? It's between them. Right? So anytime you have a 0 kind of in the middle, it's a captive 0, that is always going to be significant. The other time a 0 can be significant is when they are at the end of a number after a decimal point. So do you see there's a decimal point here? That decimal point makes this 0 significant. So I call these trailing zeros. So trailing zeros are significant if there's a decimal point. So we have 32.410. So since there's a decimal here, that 0 is significant. And it's important that these trailing zeros are only significant after a decimal point. And we'll see that in just a second. Here's when zeros are not significant. Zeros are not significant when they are at the beginning. Do you see that these are at the beginning of some numbers? So like this is a number that's smaller than 1. right? And so these zeros at the beginning, they are just placeholder zeros to make sure the 3, the 2, and the 1 end up in the right spot. So those zeros are not significant. Those are called leading zeros, zeros in the front. They are not significant because they are just placeholder zeros. They're making sure the real numbers end up in the right place. They're also not significant if they're at the end of a number without a decimal point. Do you see? No decimal point in this number, so the trailing zero is not significant. This is also a placeholder zero, so that the 6, the 9, and the 2 end up in the right place. Okay, so these zeros shown on this slide are not significant, whereas these zeros are. So captive zeros are significant, and trailing zeros after a decimal point are significant. Leading zeros are not significant, and trailing zeros without a decimal point are not significant. Okay, so like I said, zeros are sometimes significant and sometimes not. The zeros are what mess people up. Okay, so make sure you get these rules down. When in doubt, to figure out if the zeros are significant or not, you can use scientific notation, which we'll talk about more at the end of this lecture. So, to review, non-zero digits always count as significant figures. So like all of these, you see none of these are zeros, so therefore all of these are significant, and this has 4 sig figs, 1, 2, 3, 4. Okay, leading zeros, zeros in the front, like this, those are not significant. Those are placeholder zeros to make sure the other numbers end up in the right place. So this number only has 3 sig figs, the 4, the 8, and the 6. So leading zeros, not significant. Captive zeros, one that are trapped in the middle, those are always significant. Okay, so that one there, this now has 4 sig figs, 1, 2, 3, 4, because that captive zero is significant. Trailing zeros are the ones that are exciting. Okay, trailing zeros are significant only if there's a decimal point. So like this number, do you see there's a decimal point there? That makes these trailing zeros significant. So there's 1, 2, 3, 4 sig figs. However, if we have this one, do you see no decimal point? This only has 2 sig figs because now these zeros are not significant. So the trailing zeros are what get people in trouble because they are sometimes significant. If there's a decimal point, yes, they're significant. No decimal point, not significant. Okay? So let's try this out. How many sig figs in each of the following? So here's one. So looking at this, we know the 1 and the 7 are significant because they are, non-zero digits. It's the zeros that we need to worry about. Do you see these 2 zeros here? Those are captive. So they are always significant. They're between the 1 and the 7. So those are always significant. The real question is this zero significant? So it's a trailing zero. That's one where it's like sometimes significant, sometimes not. Remember, trailing zeros are significant if there's a decimal point, which there is. So since there's a decimal point, this one is significant. So all 5 of those digits are significant. So there are 5 sig figs in this number. Let's try this one. All right, so the only thing we need to figure out is that 0. So again, that's another trailing zero. Trailing zeros are significant if there's a decimal point. So since there's a decimal point, it is significant, so this has 4 sig figs. Alrighty, so we have some captive zeros. Remember, captive zeros are always significant, so those 2 are. But we have another trailing zero. Remember, trailing zeros are significant if there's a decimal point. Do you see there's no decimal point in this number? Therefore, that 0 is not significant. So this number only has 5 sig figs. So I want to be clear though, that 0 is still important. It makes all of the numbers be in the right place, right? But when we're looking at how precisely we know something, it's not significant in terms of precision. So it's important to make sure all of our numbers end up in the right place. That's why we call it a placeholder zero, but it's not significant in terms of a measurement. All right, let's look at this one. This is scientific notation, even more exciting. In scientific notation, what's really cool is it's only ever going to show you numbers that are significant. We don't need to worry about like this stuff. This doesn't play into our sig fig stuff. The number here, that's what we need to look at for sig figs. Okay, so they're only going to show you numbers that are significant. So this has 3 sig figs. All of those are significant. All right, let's check out this one. So we got some more zeros happening, right? Do you see these zeros are at the beginning of the number? So these are called leading zeros. They're another form of placeholder zeros. Leading zeros are never significant. So this only has 2 sig figs. All right, last one. So now we have a bunch of zeros. These zeros are all trailing zeros. Remember, trailing zeros are only significant if there's a decimal point. No decimal point here, so those zeros are not significant. So this only has 2 sig figs. Alrighty, let's practice this. Go ahead and pause here and complete problem number 5 on the Chapter 4 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, so it's important when we're starting to talk about calculations to talk about rounding numbers. When you do, a calculation in a calculator, your calculator is going to tell you a bunch of digits, right? And your calculator doesn't know anything about significant figures. So it doesn't know how to round your answer correctly to the right number of significant figures, and it also doesn't know to round up or round down. Right? In this class, we have some rules to follow with calculations so we know how precisely we know a measurement or how precisely we know the result of a calculation. Okay, so I want to be super clear. When you punch things in your calculator, don't just write down what your calculator says because it may tell you more digits than you can actually record. So we're going to learn some rules as to how many digits we actually write down. Okay, so those extra digits that we don't need, right? Say we need to round something to 3 digits or 4 digits. We are going to just kind of knock those off, and we may need to round that last number up or down depending on what it is. Okay, so the value of the last digit, we will use this rounding off. And you've likely heard about rounding before. So our rules for rounding off. If the digit after the number that you're going to keep is less than 5, so let's say here, we just needed to record 3 sig figs, so we're going to chop this off, okay? Do you see that 3 is less than 5, okay? If it's less than 5, then you just chop it off and get rid of everything else, okay? And you're just going to drop them. That last digit doesn't change. But, again, let's say we're keeping three digits. See, this 8 is greater than 5, so we need to round up the 7, and we'll record 11.8. Okay, so since this 3 was less than 5, it didn't round the 2 up. Since the 8 is greater than 5, then it rounds the 7 up. So be careful there. Make sure you're not just chopping off your number out of the calculator. Make sure you look and see, do I need to round up or not? Okay. All right, let's try some rounding. So if we rounded this to 4 significant figures, so 1, 2, 3, 4. So we're going to chop it off here. We look at the 7 and we say, hey, that 7 is greater than 5. So it's going to round this 3 up. So we would write 79.14 because that 3 got rounded up. This one, if we were rounding to 3 significant figures, remember, leading zeros are not significant. So 3 sig figs would be 1, 2, 3. So we're going to chop it off here. Okay, that 5 is going to round the 4 up. So we get 0.0435. All right, let's try another one. If we're rounding to 3 significant figures here, then we're going to chop it off right there, right? So the 2, because it is less than 5, does not round up that 6. So we just write 136. And I want to make a note here. If you're using Alex for your homework, sometimes it'll make you put in the answer as 136 point to show that it's exactly 136 to that number of significant figures. That's fine. You can do that for Alex. You don't need to do that out in the real world. We know that this is the same, saying that we have 3 significant figures. All right, let's look at this one. If we round this to 2 significant figures, remember the leading 0 is not significant, so we're going to round it to here, 1, 2, and that 9 rounds up the 7, so we get 0.18. All right, go ahead and pause here and complete problem number 6 on the Chapter 4 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, let's start doing sig figs with calculations. So since all of our measurements that we're making involve uncertainty, right, we have to be able to kind of correlate that uncertainty with the correct number of sig figs in our calculations. So we make a measurement, we have some numbers, right? And they're rounded to a certain number of significant figures to tell us a certain precision. Once we do some math with it, we have to round them again so that we keep that level of precision. Because like I said, when you put numbers in a calculator, it's just going to spit out a bunch of numbers, right? And it may spit out more numbers than you actually should report to kind of correspond to our uncertainty in our measurement. So when we're looking at significant figures in calculations, the rule of it is the results of a calculation are only as precise as the least precise measurement. And I think that makes sense. If we don't make a very good measurement, then if we go and do some math with that measurement, we can't make it more precise than our measurement started off, right? We have to keep that same level of precision after we do math with that measurement. So that's what we're going to look at here. Our rule for multiplication and division are just going to be based on total number of significant figures. So by that I mean, do you see this number? This has 3. The 7, the 9, and the 2 are all significant because they're not zeros. So that has 3 sig figs, whereas this number only has 2. If I put it in the calculator, I get this. But it came from 3 sig figs and 2 sig figs. So we actually have to round this. Our answer can only contain 2 significant figures because there are 2 in this one. Okay, so when we're doing multiplication and division, we're going to look at the number of significant figures in the numbers being multiplied or divided. So this one has 3, this one has 2, and we're going to look at the number that's smaller. Okay, so since this number has 2 significant figures, our answer has to be rounded to 2 significant figures. Okay, so our answer needs to match the precision of our least precise measurement. Okay, so let's try this out. Here's a calculation. So this first one, this has 3 sig figs and this has 2. So if we put this in our calculator, we get that. But that's 4 sig figs and we have to match the least precise measurement. So we'll round this to 2 significant figures. So we're going to kind of chop it off here. Remember that 6 is going to round this 2 up. So we'll get 23. Okay, let's try another one. So here we have 4 sig figs versus 3 sig figs. If we punch it in the calculator, we get this, right? Which would be really precise, but it's not, right? We have to match our least precise measurement. So we can only keep 3 significant figures. So again, that 9 rounds up the 1 and we'll get 4.22. Okay, let's look at this one. So remember, leading zeros are not significant, so this only has 1 sig fig and this has 4. So again, we're going to match the precision of our least precise measurement and we're going to only keep 1 significant figure. Remember, leading zeros are not significant, so we're going to chop it off right there. So the 7 rounds up the 4, and we get this. Alrighty, so this, remember, trailing zeros are not significant unless there's a decimal point. No decimal point here, so that 0 is not significant. So this only has 2 sig figs, and this one has 2 sig figs. So when you punch this in our calculator, we get that, so we have to chop it off here. Okay, this 6 is going to round up the 3, so we get 240. Be really careful here. It's really common for people to be like, oh, I chopped it off here, I'm just going to write 24. And it's not, though. You still have another digit here, right? So we need to include this placeholder 0 to make sure the 2 and the 4 end up in the right spot. I like to think of it this way. If, let's say you had $236.666667, okay? And then you rounded 4 significant figures to 2 sig figs. 237 essentially rounds to 240, right? But if somebody instead handed you $24 instead of $240, you'd be pretty ticked off, right? That placeholder 0 is important to make sure the 2 and the 4 end up being 240 and not 24. So any non-significant places like that, we're going to include a 0 that's a placeholder 0. So be careful with ones like this to make sure that you write down 240 and not 24. All right, here's another one. So here we have 5 significant figures versus 3, so we need to have 3 sig figs in our answer. So again, 1, 2, 3. So we're going to chop it off right there, sig fig wise. The 2 does not round up the 7. So we're just going to keep the 7 as it is. But remember to include that placeholder 0 to make sure the 5, the 8, and the 7 all end up in the right spot. All right, last one. This one has 4 sig figs versus 3. There's what our calculator says. So we're going to round it to 3 sig figs. 1, 2, 3. And that 8 is going to round up this 8. And we get 0.359. For now, don't worry about the units. We'll get more into units later. I'm just worried about, can we round to the right number of significant figures in these calculations? But for multiplication and division, like we've been doing here, you're just going to look at the total number of sig figs in each of the numbers and then round to the least precise number of significant figures. All right, go ahead and practice this. So we're going to do problems 7A through D on the Chapter 4 lecture worksheet. Go ahead, try those, and then come back when you're ready to move forward. Alrighty, so that was multiplication and division. We have different rules for addition and subtraction, but the reason behind it stays the same. The results of a calculation are only as precise as the least precise measurement. So the way that this shows up in addition and subtraction is, I call this the digits past the decimal rule. Okay? The digits, the answer of our calculation cannot have more digits than our least precise measurement. Okay? So let's take this example. It's easier if you see an example. Do you see here, if we were going to add up all these numbers, this has 2 digits past the decimal, this has none, and this has 1 digit past the decimal. So if we're looking at the one that's the least precise, that's this one, because it has no digits past the decimal. Therefore, our answer cannot have any digits past the decimal. The easiest way that I have found to do this for addition and subtraction is to do this old school. And I know people don't like to do this. They're like, I just want to plug it in my calculator. Do this so you know the right number of significant figures. If you add them all up with the decimal point in the same place, you can draw a line for where the least precise measurement ends, right? The 79, that's the least precise measurement because it has no digits past the decimal. So if I draw a line right there, the same has to be true for my answer. Okay, so if I add these all up, then we get that 9 rounding up the 6, so our answer is 247. Okay, so this is the digits past the decimal rule. Addition and subtraction, we're going to think digits past the decimal. Digits past the decimal, okay? So let's try these out. Here's our calculation. We have 2 digits past the decimal versus 1 digit past the decimal. So this is what we get in our calculator, but we have to match our least precise measurement. So we can only have 1 digit past the decimal here, so we have to round our answer to 1 digit past the decimal. The 4 does not round up the 2, so we just chop it off at 10.2. All right, let's look at this one. Again, we're going to think digits past the decimal. This one has 1 versus 2. So when we punch this in our calculator and it looks like this, we say, okay, but I can only have 1 digit past the decimal. The 7 rounds up the 2, so we get 76.3. All right, here's another one. This has 2 digits past the decimal. This has 3. So when I plug it into my calculator, I have to match my least precise measurement with 2 digits past the decimal. The 1 doesn't round up the 9, so we just chop it off. Here's another one. 1 digit past the decimal versus 3 digits past the decimal. So here's what our calculator says. Again, we have to match our least precise measurement, so only 1 digit past the decimal. That 2 does not round up the other 2, so we just chop it off. Here's another one. 1 digit past the decimal versus 2. So this is what our calculator says, but we can only have 1 digit past the decimal. The 7 rounds up the 5, and there we go. One more. We have 3 digits past the decimal and 3 digits past the decimal. So when we punch this in our calculator, we get this. And you're like, wait, I need to have 3 digits past the decimal. You're right. Your calculator actually got rid of that 0. That's important, okay? So it's not always just chopping it off. Sometimes your calculator doesn't know, hey, that 0 was important, okay? And you need to add it back in. So it's really important in this class that you are smarter than your calculator. Your calculator doesn't know how to round to significant figures. So you need to make sure that you round your answers correctly. All right, let's go back to number 7 on the chapter 4 lecture worksheet and do problems number E through I. Once you're ready to move forward, come back and we'll keep going. Alrighty, so we learned the rules for multiplication and division, and we learned the rules for addition and subtraction. But what if they're all happening in the same problem, like this one, okay? And I say, round the following calculation to the correct number of sig figs. Well, the first step we need to do is to deal with the subtraction on the top. When we deal with the subtraction on the top, remember, now we're following the digits past the decimal rule. Addition and subtraction are digits past the decimal. So we stack them up. We have 2 versus 1, so our answer needs to be rounded to 1 digit past the decimal. So that 8 rounds up to 9, which actually goes and rounds up to 6, so we get 7.0. Okay, so we followed the digits past the decimal rule, which makes now our problem look like this, because this math ended up being 7.0. So I'll just plug that in for that up there. So now when we look at division, like is happening here, division is total number of sig figs. So on the top, we have 2 sig figs versus 3 sig figs. So our answer has to be rounded to 2 significant figures. Okay, so it'll end up being chopped there. That 3 doesn't round up to 9, so we get that. So if we have, both addition and subtraction and multiplication and division in the same problem, we have to follow the first rule, one of the rules, round to the correct number of significant figures according to that rule, and then change rules and round to that number of significant figures. See, isn't this fun? I know you guys are going to have fun. It requires a little bit of practice, but you will get better at it. All right, we do have a practice problem on this, so go ahead and try problem number 7J on the chapter 4 lecture worksheet. When you're doing these, I just want to remind you that the answer key is available on Canvas. So go ahead and check it out and make sure you're doing these correctly so you don't practice it incorrectly. All right, once you're done, go ahead and come back and we'll keep going. All right, our last topic of today is scientific notation. So scientific notation is a way to write very large or very small numbers in compact form. And what's important here is usually these are used for measurements. And when we use them for measurements, this number at the front is going to tell you all of the significant figures in your number, which is really nice. So it's easy to see this has 4 sig figs because there's only 4 numbers there. The way that scientific notation works is that this first number is always going to be a number written from 1 to 10. So there can only be one number in front of the decimal point, and it's going to be a number from 1 to 10. It can have as many numbers past the decimal point as you need, but there can only be one number in front of the decimal point. And then it's always going to be raised to some power. It's either going to be a positive number or a negative number. Okay? So if we look at this one down here, 23 times 10 to the 5th is not in proper scientific notation because there's no decimal point here, right? I told you there can only be one number in front of the decimal point. Here, there's trying to be 2. So we would rewrite that as 2.3 times 10 to the 6th. And we'll learn about how to do that later. But this is not correct because there's no decimal point. It has to be a number between 1 and 10. All right, so let's learn how to write a number in scientific notation. So we're going to move the decimal point in the original number so that it's located after the first non-zero digit. So essentially, like if we look at this previous slide, if we said, 23 times 10 to the 5th, we would move our decimal one place so that there's only one number in front of that decimal. So we're going to move the decimal so that it's located after the first non-zero digit. And then you're going to always have, you can have a number and then it's times 10 to the something. Okay, always, always, always. It's a number times 10 to the something. And that something is going to tell you the number of decimal places that it moved. How many times did you move your decimal point? And your exponent is going to tell you which direction it moved. Did it move to the left or did it move to the right? Or is it talking about a big number or a small number? So these positive exponents, if your exponent is a positive number, that tells you your number is really big, okay? And you're going to move it to the right to convert it out of scientific notation. If you have a negative exponent, that tells you your number is super small, and you're going to move it to the left to convert it out of scientific notation. Okay? So these are just kind of helpful hints. We're going to go through some examples of these. Like this one. Write 0.000423 in scientific notation. All right. So the first step is to move that decimal point. So we're going to take it here, and we're going to go 1, 2, 3, 4, right? And we have to put it so that there's just one number in front of the decimal point. So that's going to give us 4.23, okay? The decimal was moved 4 places, so our exponent is going to be a 4, okay? I think that makes sense. We went 1, 2, 3, 4. We moved it 4 places, so our exponent's a 4. Do you see that this number was really, really small? So therefore, we are going to make this a negative exponent, like this. Anytime you have a negative exponent, that's telling you it came from a really, really small number. You can also think about it, if the decimal was moved to the right, so it's negative, but I think that starts to get a little bit messy with the whole left and right business. I like to remember, if it's a really small number, it has a negative exponent. If it's a really big number, it has a positive exponent. And I think that's going to be a lot more logical as you move forward. Let's try this one. Convert these numbers into scientific notation. So 4,000. So again, we're going to pretend like our decimal point was here, and we're going to move it 1, 2, 3, so that it's after the first non-zero digit. So we're going to get 4 times 10, and then we moved it 3 places, so that becomes a 3. And it's positive because 4,000 was a big number, right? It's bigger than 1, so it's a big number. Let's try this one. Okay, so we're going to pretend our decimal point is here. We're going to go 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're moving it 8 places. So this is going to be 3.06 times 10 to the 8th. Again, this is going to be a positive exponent because 306 million is a big number. You'll notice that I'm not keeping, like when we look at 4,000, those zeros are not significant. Those are placeholder zeros. There are no decimal points in that number, so those zeros that are at the end are not significant. So they're not showing up when I put this into scientific notation, because scientific notation only shows significant numbers. Same thing here. When I moved this decimal to right there, I got rid of all of these zeros that weren't significant, because scientific notation only shows significant figures. But this 0 in the middle had to stay because it is significant. Let's look at this one. So we're going to move this decimal 1, 2, 3, 4, right? So we moved it 4 times, so we get 8.82. And do you see that now this is negative? Because this number was really small. It's smaller than 1. So we get a negative exponent to indicate that it's a very, very small number. And again, we didn't keep those leading zeros because they're not significant. Here's another one. We move our decimal point 7 times. And again, this is going to be a negative exponent to show that that's a very, very small number. All right, let's do the opposite now. Let's convert numbers out of scientific notation. All right, so 2.48 times 10 to the 3rd. So remember, the fact that it's a positive exponent tells us that this is a very large number. So we need to make this be a large number. So we're going to move the decimal point that way. So we're going to go 1, 2, 3. Okay, so when I do that here, I'm going to write it up here. When I move this 3 places, 1, 2, 3, you see there's no number right there? I'm going to put a 0 there. Okay, so this ends up being 2480. So that 0 wasn't present in the original number because it's not significant. It's a placeholder 0, but it's important here to make sure the 2, the 4, and the 8 all end up in the right place. Let's try this one. So again, the fact that this is a positive exponent means that this is going to be a very large number, and we're going to move this 6 times. So 6.123. Okay, so again, we go 1, 2, 3, 4, 5, 6, and we're just going to fill in zeros for the rest of these. Okay, so again, those zeros weren't there in that number because they're not significant, but they are important placeholder zeros. Let's try this one. Now, do you see we have a negative exponent? Since we have a negative exponent, that's telling us it's a very small number. So we're going to move the decimal point the other way. So it was here. So we're going to go 1, 2, 3, 4, 5. So that's where our decimal point ended up. I'm going to put a 0 in the front and then fill in all of the other zeros. Okay, so it looks like that. Your turn. Convert these numbers into or out of scientific notation. Try these out. Once you're ready, come back and we'll go over them. Alrighty, let's do the first one. So this is times 10 to the 5th, so that tells us it's a very, very large number. So again, we're going to take our 1.23 and we're going to move the decimal 5 times to make it a large number. 1, 2, 3, 4, 5. So we're going to fill in our zeros, and there you go. Same thing with the one at the bottom. Very, very similar, but you're going to move it 6 times instead. All right, let's do this next one. So we need to convert this into scientific notation. So we're going to take our decimal from here, and we're going to move it 1, 2, 3, 4, 5 times, so there's only one number in front of it. So that's why this is a 5, because it got moved 5 times, and it's a positive number because this started off as a very big number. Okay, and again, we dropped those zeros because they are not significant. Same thing with this one. You're going to take this, and you're going to 1, 2, 3, 4, 5, 6, 7, 8. And again, those ending zeros got dropped because they are not significant. Same thing with this last one. All right, let's look over here on the right-hand side. So now we need to convert this one into scientific notation. So we're going to move this 1, 2, 3, 4 times. Since we moved it 4 times, this becomes a 4, and it's a negative 4 to indicate that this was a very small number. So this one, when we convert this into scientific notation, because that's a negative 6, we need to make it a very small number. So we're going to move it to the left. So we go 1, 2, 3, 4, 5, 6. That's where our decimal is. And then we're going to fill in all of our zeros. Okay. Same thing with the one below it. Fill in all of your zeros. This here, we're going to move it 1, 2, 3, 4, 5, 6 right there. And so this becomes a negative 6 to indicate that it came from a very small number. Same thing with the bottom one. It'll be a negative 4 to indicate it was from a very small number. Alrighty, go ahead and complete problems number 8 through 10 on the Chapter 4 lecture worksheet to get some practice doing these numbers in and out of scientific notation. And this actually wraps up our first lecture on Chapter 4. We covered a lot of ground today. We talked about exact numbers versus measured numbers, and we said in measured numbers, there's always some level of uncertainty because we always had to estimate that one digit past what there was a line for, right? And since we have that estimating that's happening, we have to round to a correct number of digits. And when we do that rounding after a calculation, right, we need to be smarter than our calculator. If we have, multiplication and division, we're going to round for total number of sig figs to match our least precise measurement. If we have addition and subtraction, we're going to look at digits past the decimal point and round to the correct number of significant figures to match the least precise measurement. And then we started talking about scientific notation. In chemistry, we use a lot of numbers that are very, very, very big or very, 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 very small. And it's helpful to write these numbers in scientific notation so we don't accidentally drop a 0 along the way in our calculations, and it also saves us, kind of space on paper. So we covered a lot of ground today, but this is setting up our foundation for doing mathematical calculations in chemistry, which are a very important part of this class. So keep practicing, get lots and lots of practice doing these calculations, especially sig figs. I know that people get tripped up on those. If while you're working, you're looking at the answer key and you ever have any questions, please send them my way. I'm more than happy to help you out. I'm here to answer any and all questions that you have. Otherwise, keep working hard, and I will talk to you guys next time.